All right, welcome everybody to our February 2026 Lunch and Learn series entry. We're going to be talking about the Spacetime library. There's a QR code in the bottom of the screen here. If you are interested in joining MEGUG, then you can go ahead and snap that QR code. It will be here throughout the introductory slides until I introduce the speaker. Want to save the date for a couple of things. Our next Lunch and Learn will be, whoops, and this is doing what it did the last time. Our next Lunch and Learn is tentatively on March 11th with a rain date of March 25th. It will be an introduction to GeoAI with Dr. Wang from University of Maine. He's a new faculty in spatial informatics that will talk about the GeoAI revolution. Also want to save the date. We have the Maine Municipal Association Technical Conference coming up on May 13th. We'll have a MAPI hour and a session at that event. So for those who are interested, keep that date in mind. I'd like to thank our sustaining members. And this, we got to figure out why these slides are doing this. This is weird. We have CAI Technologies, Esri, the Maine Technical Source, and Viewshed. Our silver sustaining members, the Department of Agriculture, Conservation, and Forestry from the state of Maine, the Maine Department of Transportation, Maine Office of GIS, Maine Public Utilities Commission, the University of Maine's Raymond H. Folger Library, the University of Maine's Wheatland Geospatial Lab. Our bronze sustaining members, the Maine Geo Library, CGIS Solutions, Deergo Spatial Systems, the Greater Portland Council of Governments, GEI Consultants, the St. George Consulting Group, Stantec, Stone Environmental, Wright Pierce, and the Kennebunkport and Wells Water District. Without further ado, I would like to introduce our speaker. Our speaker is Alex Burnham from the University of Vermont. Alex is a data science and computer programmer in the Department of Biology there. We have worked together on various things as part of an NSF EPSCoR grant about spatial and temporal data and the revolution that comes with that and what we can facilitate in things like agriculture and ecology from that. So Alex is going to talk to us about the library that was constructed as part of that called Spacetime that works in both R and Python. So with that, I will just say if you have questions, Becky and I are here to process those. Please put them in the Q&A and we will address that. And other than that, I will turn it over to Alex and we'll handle questions at the end.
Great. Thanks for that intro, Matt. I'll go ahead and share my screen and pull up the slides. Okay, so as Matt said, I'm going to be talking about a library called Spacetime, and the title of this talk is Lowering the Barrier of Entry to Spatio-Temporal Data Through a New Library. This was done with work collaboration between the University of Maine and University of Vermont through the Barracuda project, which was an EPSCoR grant funded through NSF, and it was, as I said, hosted between the University of Vermont and UMaine. So I'll talk a little bit about the roadmap that we're going to have today for this talk. I'll talk very quickly about my research background and how I got into doing this work. And then I'll talk about spacetime itself. I'll introduce spatio-temporal data cubes. It's going to be very quick for this group because I'm sure you all know as a GIS group all about that. And I'll talk about the workflow and syntax, and then talk about a case study that came out of this grant called the Delta method. And then I'll do a quick code demonstration. We'll jump out of the slides and show how it works in person. And then I'll talk a little bit about the future work around spacetime and how we're hoping to integrate it and then continue it after this grant has ended, which it has ended as of 2025. So trying to keep software alive. My background as a data scientist at UVM was mostly with disease ecology, data science, and working with disease in bees, bumblebees, honeybees. That's how I started working in the computational world. So in general, I like to focus on a combination of empirical data, computational tools like network theory, mathematical modeling, to ask questions about biological systems. So a lot of the work I do will be some combination, some synergistic combination of field studies, laboratory studies that inform parameters and computational models that we can then use to experiment with and ask new questions. Project examples, measuring baseline data for bee disease and pesticide exposure, testing and modeling RNA virus transmission routes between honeybees and bumblebees, exploring novel approaches to building realistic synthetic contact networks for modeling transmission, and then testing how migratory beekeeping might affect disease transmission, queen breeding for hygienic behavior that bees might exhibit to actually try to stop disease transmission on their own, and then things like co-infection, understanding how agent-based disease transmission that might spill over from shared flowers would happen in a spillover event. So you can see that the majority of this is all around disease transmission, mathematical modeling. That kind of is my data science background in this. And there wasn't really a spatio-temporal GIS mapping component until I started working for this grant, the EPSCoR grant, and was tasked with designing and building a computational toolkit for making spatio-temporal raster data easier to merge and use for the average ecologist who is a programmer, but maybe is not trained in GIS. And so as somebody who wasn't officially trained in this field, it was actually a cool experience to start from the ground up and then work my way into it. So for 5 years, I was working on the grant, working on other models as well, but in the background, always working on Spacetime. So this grant, as I said, was funded through Barracuda, an EPSCoR grant, and it stood for Biodiversity and Rural Adaptation to Climate Change Using Data Analysis. So sort of a rough acronym there. So we did a lot of work modeling range shifts of trees, songbirds in the light of future climate change, and as well as crop and agricultural changes that would be happening in rural areas as well, and how those things are related to each other and how that affects the actual human population. This was the team, a great team. This is us meeting halfway between UVM and UMaine, which we did every summer. We had great working meetings there and were able to get a lot of work done. We wrote almost an entire grant directly here one year, which was great. So very productive. But there's the great team, and they all helped contribute to this in one way or another. So the specific goal here is to develop a computational toolkit for scaling and merging spatio-temporal data that takes a lot of the coding and control structures and kind of the more coding aspect of it out of the equation and makes it more just a library that any functional programmer can use. So let's introduce Spacetime here. So Spacetime deals with spatio-temporal data. As we all know, we might have a lat-long slice here. In this case, it's a choropleth, but it could be a pixel-based raster. We have multiple slices through time, and we want to create a nice temporal stack where everything's aligned and make it so that each of these points along these three indexing variables leads to some data set that we can access. Commonly stored as raster files, things like TIFF, NC4, PNG, JPEG, they're all image files, all rasters. More commonly in the geospatial world, as you know, we'll deal with NetCDF and GeoTIFF that specifically contain metadata for actually mapping these points onto a spatial location and kind of spherifying a flat plane. But there's lots of dilemmas that come out of this, and specifically I'm thinking about from someone who is an ecologist, doesn't have formal training in GIS, and wants to start incorporating data sets that relate to climate change or other raster data as covariates into their models or something like that. The more we're finding out about climate change and how it affects things, people who studied things like evolution and speciation and things like that separately, realizing that actually climate change influences this much more than we previously thought. So it's becoming a more common thing that needs to be brought into most research programs. But it's big data. There's storage issues. There's the computational overhead of working on large data sets like this. And then, of course, there's the dimensionality. So if you're finding data sets that you need to actually incorporate into your models, they might be different file sizes. They might have different spatial reference systems, and they might be structured differently. Here's 3 different kind of spatio-temporal or d-dimensional data stacks that are structured in a very different way, but could be handled very similarly if you had the tool set to do it. For biodiversity surveys, we often have time points and sites. And then the species are actually linked together with some sort of metadata that's associated with a phylogenetic tree or something like that, some sort of relatedness. We have ground instruments, which might measure different things like temperature, pH, and light, and store those as separate raster files that each have a site location and a time component as well. We might have remote sensing, which is the more traditional three-dimensional space-time cube that I tend to think of. So you have latitude, longitude, and time. But there's tons of different spatial reference systems, different ways of taking a flat thing and wrapping it over a sphere. So there's a lot to learn from this in this field. There's the temporal and spatial alignment component as well. So if you have everything, all these layers, you need to make sure that all the grids line up, they're the right size, and that's a non-trivial task for the average user. So the way we're thinking about cubes in space-time is pretty simple. We have these three indexing variables: time, longitude, and latitude. In most cases, they can be other things as well, but we'll restrict it to this for now. It's ideal for storing spatio-temporal data because at each of these points, this intersection between these three variables, we can store some sort of datum, some variable. But it can also be higher dimensional, d-dimensional. So you could store more than one thing at each of those points. And however you want to think about a higher dimensional cube, multiple cubes that are linked together, or a single cube that has higher dimensional structures within each of those three intersections. But we have the ability for easy higher dimensionality. And then we also have quick vectorized operations between cells. So we could do cell-wise mathematical operations. We can even, multiply things, take the average of multiple cubes, scale things by scalar values. All of the kind of matrix linear algebra operations are all possible with these kinds of structures. So it's a very useful structure, and it's the way we finally settled on dealing with it in space-time. So we have our index variables, and what we'd like to have is something like lat long time. And then at some point where those intersect, we have a value for something like temperature. Or higher dimensionality, we have some sort of list of multiple values for temperature, humidity, precipitation. So those could all link into there. But what we more often have, and what as an ecologist would be my nightmare, would be tons of different raster files with different spatial reference systems, different grids, different extents, different file types that all have different metadata stored in different ways. What you want is to line them all back up and trim them into something, and then convert them into some sort of unified stack or cube that you can then do that math to. You can add x cubed to y cube and raise it to z cube, or take the mean of x cube and y cube and get the average of those two data stacks. But that's, again, a non-trivial task unless you've been formally trained in working with raster data. So that's where spacetime comes in. As Matt mentioned, there's two versions. There's one for Python and one for spacetime. Python is kind of the native version of spacetime. Spacetime is written in Python, and the R version is actually running the Python code underneath. I'll talk a little bit about the Python version first. So it's currently hosted on PyPI, so you can go install it now. It's live and being updated. Information can be found at this GitHub site here. That's where I'm keeping things like access to the API and information on notation and syntax all can be found there. All of the information you need to actually use it. So like I said, it's written in Python and it's based on Goodle. So it's using Goodle underneath for all of these the spatial work, the work functions and things like that. The R version can be installed via GitHub, and it actually can be used in RStudio or Positron with R syntax and output R objects using the reticulate package. So that's how it's running. And it actually runs almost just as fast as the Python version. There are some sticky issues that happen with the difference between Python and R objects, but once you get used to it, it behaves just like any other R code. It is updated less frequently, so I kind of wait until I've got a Python version that I'm really happy with, and then I go through the effort of porting it to the R version and then updating that one. So the Python version will be always likely to be the most up-to-date version. And I think it's the easiest to use, the most um, uh, uh, friendly way of downloading it. You just pip install it or and then work right with it directly in Python. So kind of the high level overview capabilities of Spacetime as it stands right now is it can read in common raster data types, most of the ones that we would be dealing with, rescale files to a common spatial reference system and grid size, trim data sets to the same bounding box using a shapefile, unions, intersections, corners, anything like that. Select and rescale those data along the time dimension so you can expand, shrink, select different time slices as you go. And then, of course, you can do mathematical and functional based operations to those cubes. So if you had a model that had, a couple of spatio-temporal cubes that needed to be averaged, and then, anything that you could think of doing, or if you wanted to pass it a function or a user-defined function, then you can pass it to that, and that will actually do the cube operations and pass out the resultant cube from that. We can return the cube using a tabular format or a data frame. That's very common for plotting and things like ggplot. They kind of require data frames. It can be difficult with really large cubes because the data frame would be extremely long, but it is possible and something that I felt like it was important to include. And then there's some plotting software built into Spacetime. It's more of a exploratory plotting software. It's using Plotly, so it's kind of you're able to hover over things and see what values are. It's kind of a good way of seeing that, making sure that the operations that you did resulted in the way that you expected them to, and kind of do that kind of diagnostic work, but maybe not necessarily publication-ready graphics. Okay, so let's talk about the workflow that we've incorporated into Spacetime. There's kind of two basic stages. So if we're starting out with a bunch of unprocessed raster files, say in a list, we first want to read them into the Spacetime environment, and we do that using read data. So the read data function will create a Spacetime file object. Now this file object can be queried. It has a lot of attributes that you can query and extract data from at this point. But again, these are just going to be the unprocessed files at this point. So you can query the EPSG code and see if there's differences there, see what's happening to the scale with the scalings and extents of these files, and see what you need to do to actually get them all back into shape. And then you would actually go ahead and use your raster align and raster trim functions, which have a lot of different methods associated with them for picking your pixel size, making sure that you're trimming or finding the union, or using a shapefile to get those kind of cookie cutter through those layers once they're aligned and scaled the right way. But that would be done at this point. And then you would have a cleaned file object. So this is still a file object. It's still a list of these rasters, but now they all are unified and uniform, and they have the same structure, the same reference system, same grid size, same extent, etc. They all line up. This is where we enter the next stage. We use the makeCube function, which tells Spacetime how to arrange those cleaned cubes into the new, or those cleaned rasters into the new cube. Are they all time points? Are they different variables? Are there different bands within each raster? How are we going to structure this resulting cube? And then we end up with a cube object, which is now written to disk at this point as a netcdf or as an NC4 file. And now we can do kind of cube-based operations to this here. So now that we have a clean cube, we can scale time. We can plot it to look at how it's structured. We can look at summary statistics of it over time. We can expand time, shrink time, select time slices, and then do any of those kind of functional or mathematical operations to them here as well. So you could modify that cube object, and then you could use makeCube again to write that new cube out to the environment. So you could write a new file to disk there. So we kind of have these two sets of operations here, these pre-cube operations, which is where we're actually getting everything in shape so that they'll work well with each other. And then we create that cube, and then we get into those cube operations where everything is clean. We can scale time. We can go ahead and add them together or do whatever we need to do depending on what our goal is here. So we kind of have this cleaning point and this scaling, this cube-based point here there. So we can also read the cube in at any time once it's been written to disk and bring that whole Spacetime cube back into memory, or do it in a mosaic style. But we have Spacetime cube file, and then we just use the load cube function, which will bring that space-time object back into memory. It's lazy loading, so it won't pull the whole data array in at that point. So then you could go ahead and query, do some more scaling, then make that new cube and write it to disk, and just kind of rinse and repeat. Makes it good for being able to work in chunks and then push things to Git and then come back and work again. Or if you're working with a group, you could pass a cube to somebody that you scale. They can make some modifications to it and then send it back to you. So it makes it handy to be able to load that cube back in directly as its own file object and get it into that spacetime environment. So let's talk a little bit about the structure and syntax. I'm just going to briefly go over these functions. There's not that many functions in this library, but they're all pretty powerful in that they have lots of methods associated with them, lots of settings that you can use to modify things, lots of arguments that you can change, switches that you can throw. So there's input functions for reading data in, loading cubes, creating cube time vectors that can be passed into the cube to explicitly add real time dimensions. We can scale things, so we can align and trim them on the spatial dimension. We can expand and scale and slice through the time dimension. So we also have the operations we can do to the cubes themselves. We can use the cube smasher, which is a function that you pass an equation to or pass a function to, and then pass your spacetime objects to, or even any other kind of array or scalar value or vector. And it will actually do the math that you asked it to do and output the result of the cube. Then the plot cube function, cube to data frame, we can write the cube out, and we can write out a CSV file if we're working in a tabular format. Each file object and cube object also has a series of methods associated with it. This is more for extracting and querying things about that cube or that file object to figure out what we need to do and what the actual result of our operation was. So we can, of course, always extract the original Google data. We can get things like the EPS G code, get units, get the corners, get the dimensions, pull out that data array. We have latitude, longitude, looking at the no data value. So lots of things to query here with these objects. So a quick and dirty example of a spacetime script might be something like this. You have 3 geotiff files here, file 1, file 2, file 3. They might all be arrays, single band, and there are 3 time points that you want to stitch together. So you will use the read data function, and that will create a file object of these 3 tiffs. Then you can align and trim them. That will give you a new file object where everything is aligned, trimmed, and all of the metadata and spatio, the reference systems and EPS G codes are all correct now and the same. And then you would go ahead and make cube. You would tell which files are variables, which are bands. So here we have organized files and organized bands. When organized files is files to var, that means that each file will be a different variable, and you can actually pass it variable names. And then the bands in this case might be time, or you can say bands to time, files to time, and that would mean that all of these are time dimensions that you're stitching together into one cube, which happens quite a bit when you download climatologies. They're often a TIFF for each month, and then you want to stitch them together into a 12 deep spatio-temporal cube. So I'll talk a little bit about this case study here. We were working on a project where we were looking at blueberries, and we were modeling the entire 2-year blueberry production cycle on a daily level, a daily model. And we were using climatologies to look at how blueberry production and blueberry growth might be affected in future with a future climatology, different scenarios. And we found that at the daily level, the model running at the daily level, the monthly climatologies, we could just expand them to run the same climatology for each month, but we wanted something a little more with a little more fidelity than that. And we found out about the delta method, which there's a bunch of papers on, which is a way to take a monthly climatology and daily past weather data sets and make a daily weather data for a future time point. It works well, but it has some caveats. It's not perfect, but it's better than just looping over the same month for for each day. So you have to pick a daily weather year that has properties that align with your aim. So if you're looking at a future climatology for the region of 2030 to 2040, pick your scenario. And then you also want to pick a past daily, precipitation or temperature data set that fits with what you're trying to predict. So if you're looking at what would happen in a future climate where it's very wet, you would want to pick a past year that was traditionally thought of to be very wet in your region. This assumes that the year will follow the same pattern as your past year, but shifted based on that new climatology. It's not perfect, but it is an assumption that we were willing to make, and a lot of people have been willing to make, so we went with it. But it actually involves quite a few operations, which was a great test for spacetime. So we had two data sets here just to do the max temperature version. We took a Chelsea max temperature data set for the climatology of 2030 to 2040. In this case, it doesn't really matter which scenario it was, but it was from that time range. The time scale was monthly, and the time extent was 12 months. It was a world boundary with a 4326 EPSG code, and it was scaled to degrees with a default at 0.00833. And they were a series of geotiffs, 12 of them, each with dimensions of about 43,000 to 20,000 pixels. And then for the daily max temperature data set, we went with 2019 for past weather. And the time extent was 365 days at the daily scale. And the boundary in this case was North America, different EPSG code, different scaling in meters. The file was not a geotiff, it was an NC4 file, and it had very different dimensions. So a great test for seeing if we can write simple code that would get these all to play well together and do this operation with spacetime. So we had a question apart from the actual model that we wanted to create and explore, was how did spacetime perform in this scenario, and how does it compare to just using base Goodle or using something like raster.io in terms of lines of code and runtime. So this was the entire workflow of the Delta method, looking at each data set and how it's scaled throughout this workflow. I'm breaking it down into chunks, but just to give you an idea of what's happening in this data set. And then we'll jump into some code and actually do it. So it might make more sense at that point. But we have our original Chelsea data set for 2020 to 2040. Again, 12 time slices and a world extent. We use the parameters from this to rescale our daymet data to have the same bounding box, same SRS, and same pixel size. And then we took those rescaled daymet data and we calculated monthly averages from them. So then we're averaging all of the 30, 31 days to create an average for each slice. Now we have 12 slices, a monthly daymet data set. And then you take your original Chelsea data set and you subtract the monthly daymet from the Chelsea. And that gives you monthly delta data at the time extent of 12 months. So 12 at one for each month. Then you expand that to daily. So that day will be repeated multiple times for each month. And then you add those deltas to the original Chelsea data set to get your future daily data. So there's a number of steps that have to happen here for this to work. So we tested this on 3 platforms, as I mentioned. We did Goodle, raster.io, and Spacetime coded up in Python. So I'm going to pull up the code right now, and we'll just run through it, and we'll just do a 12:30. We'll do like maybe 5 to 10 minutes of just looking at how this works. So I am in positron right now. We just switched in comp bio to using positron because we're going to be introducing Python a lot more now, and this has good support for R and Python in one IDE. So first we'll load Spacetime. So we'll import, I've already installed Spacetime with pip install Spacetime. And I'll import Spacetime as ST. And then I'm going to import the glob library because we're going to use this to get our files. So I'm going to create our path for our future files and go into that directory and grab all of the TIFFs in that folder. And then I'm going to do the same thing for the daymet NC4 file right here. So there's the path for the past data, and then I'll go ahead and grab anything in that file folder with the extension .nc. Okay, so now at this point, we just have the actual lists of files in place. So if I just print past files, just a list here in the console of these, of the single file here, in this case, the Tmax. If it was the future file, it's a list of 12 geotiffs altogether there. So we're going to enter the realm of spacetime by reading the data sets in. So st.read_data, we'll use the read data function on the future files and the past file. And now those are read in as file objects. So let me first look at the future object, and we can do a few queries here. So we can pull up ds_future, and we want to look at the band numbers here. So it's going to return a list here of 12 ones, saying that each of those geotiffs has a single band, and there's 12 of them that have been imported into this file object. Let's see what else we have here. We have get EPSG code, so we can see what we're dealing with here. So they're all 4326 in that case. And let's do one other thing. Let's look at the pixel size here. 0.00833. One other thing, we can look at the actual the spatial reference. Oop, getting an error there for some reason. That must be left over from another object. Yeah, so dimensions, for instance, pulls up the dimensions for each of those raster objects. We can do the same thing for the past files. So if I get dimensions of that, it should give me a list of 1 that just gives me the actual dimension of that NC4 file. I can also get the times here. So in this case, for this NC4 file, it's assuming that each layer in each band is a time, and we can see that I get a vector or a list from an array from 0 to 365. So that's the days there. Okay, so we're going to go ahead and align these things because they all have different spatial reference systems. The resolutions are different. We're going to use st raster align on the future and past data. We want a future cube and a past cube in this particular example. And we're going to use the method corners to actually crop them. So we're going to use upper left and lower right corners on both of these, the same values. And we're going to use the same resolution. We're going to scale to 0.0833 for both of them and force the 4326 SRS EPSG code on both data sets here. So we're going to go ahead and do the alignment and trimming here. And so that's lazy loading. So we've kind of imposed that on these files now. And when we reference them or query them, we'll get those results, but it won't be until we actually extract a data set that we actually have to wait the amount of time to do that. And that usually happens at the cube when we create the cube, where we have to actually write it to disk. So again, let's look at the past data. Oops. And we'll now get the EPSG code. And now we can see that it's 4326. So that worked. So I'm going to use the cube time function here to create times for the future and past cubes. The first one is going to be of length 12 at the month level, starting at 2024. And then we're going to have daily starting at 2019 with a length of 365 days. So we're going to create those time vectors there. And then we're going to actually make the cube. So to make the cube, we're going to organize the files so that the files are all time components and the bands within each file are also time, because we're dealing with time in both of these scenarios. In the first scenario, we want all geotiffs to be stitched together to have a spatio-temporal cube. where we have 12 monthly time points. In the other cube, we only have one raster. We have one NC4 file, but it has 365 time layers in it, and we want those all to be counted as time. We're going to pass it those time objects that we just made, so that we'll use those to actually pass the time to those objects, so they have the times that we want. If we don't do that, they'll have default times or whatever was packaged with them. But we want to, in this case, we want to give them these times. And then we're going to write the file name that the NC4 file is going to be written down to disk in, and the actual object. So here we're going to pass future into MakeCube, and here we're going to pass past into MakeCube. So this might take like 10 to 15 seconds to do. So I'll run both of those now, and we'll wait a little bit. Okay, so that finished running. Now we're going to do a little more querying and make sure that things look the way we want to. So we're going to do get dims, get the dimensions for the future data set. So we get the actual output dimensions there. This is not including the time component. And then same thing for past. So they're both 97 by 73 now. That's good. And then we can look at pixel size. That's important. So past and future are both 0.0833. So we've rescaled everything. They're all aligned. They have the same extents. So now we can actually go through and do these operations. So the first thing we're going to want to do is scale the time on the past cube to create monthly averages. So we're going to use scale time. We're going to choose the monthly scale, and the method that we're going to use is the mean, because we want monthly averages. So we'll create monthly past. And then we're going to use the cube smasher, and we're going to pass it the equation future versus past. I chose FT and PS as the variables that we want to use. And then the parent cube is going to take on the structure of the parent cube. That's going to be the default structure. And then I'm going to actually pass it the variables in those equations. So FT is going to be future, and PS is going to be monthly past. And then the file I want to write out is delta NC4. So I can do that math step. And then I want to expand the time on that delta cube to be daily. So the starting scale is going to be month, and I'm going to set target scale to day. And this will go ahead and expand that to 365 days. And then I actually have to add that expanded delta to the daily, the original daily cube to get my estimates for the daily future climatology data. So we'll do that now, another cube smasher step. And then we have that output. So we could look at all of these directly with matplotlib. So I could look at the future estimated data set that we just created here. I could get the array out and then just take the first time slice and look at it that way. Or I could go ahead and use the plotting function here. So I'm going to use space first. And I'll pull this up to make the screen bigger. So we kind of get this, I'll zoom in a little bit. Here's our raster data, and we can actually slide through the different time slices here and look at how our heat map changes. We can play it like a little video here. So we got these 12 time slices for this specific data set. And then if we actually looked at the, the daily data set, the past data, for instance, it may take a little longer to run, but here it comes. Then we'd have 365 days of the past data And again, we can look through that video and see how it changes and slide through it as well. We also have the option to look at it with a time series. So we can see the data set there, and we've got that yearly day level curve happening, and we can highlight over and look at the actual temperature value in there and what date it was actually measured in. So that's what I have for this actual case study in Spacetime. So I'll go ahead and go back into the slides and continue out that way. So what we had was here is the original data set plus the Spacetime products that came out of that case study. So the original Chelsea data set for January is in panel A, and then we cropped it and scaled using the Chelsea data set's parameters and the bounding box that we needed to use for that particular model. And then we calculated the delta values for all pixels and then estimated the future max temperatures for the years 2030 and 2040 at the daily level. So not a perfect approach, but pretty good for what was available, and Spacetime handled it well. So let's look at code length and speed comparisons between these three libraries, remembering that Spacetime is running Goodle under the hood. So you would hope they would be about the same runtime, and they are. But I wasn't convinced that was obviously going to be the case, because you can write a large program with a library underneath and still run into all kinds of problems and in the way that it was coded up, and run into memory leaks and other issues. So I was happy to see that they're behaving the same way. So that's great. But Spacetime does a lot more under the hood that you don't necessarily have to deal with. It's just sorry, my Bluetooth headphone just died. I put another one in. So there's a lot of there's a lot more code that's being needed to run for raster IO and Goodle than there is for Spacetime, as you can see for these lines of code on the red axis here. So Spacetime is achieving its goal here in that it's doing a lot of work, but it's using a lot of smart defaults and taking a lot of the coding and the looping and the control structures and hiding it under a different level, so that the user just has to interact with the API and the methods within each function, or the arguments within each function. Another way of looking at this, which I kind of like, is actually weighting the script so that these are actually they're all the same sizes, so that you can actually see the length of the script compared between Spacetime, raster IO, and Goodle. There's just a lot more stuff that needs to happen with Goodle and raster IO for a long workflow like that that Spacetime is designed to handle under the hood. So I'll just talk about some takeaways. Spatio-temporal data is all around us, but it can be hard to utilize for those of us who haven't been trained in it, and we're starting to learn that more and more people are going to need to use it in their research programs. The tools exist, so all of this could be done without Spacetime, but there's some hard learning curves and a lot to figure out before you actually get into it. So the goal of Spacetime is to reduce that learning time, reduce the coding time, and hopefully not sacrifice the runtime. And so far we're meeting these goals, but we're aware that there's always so much to do, and that software is never finished, and that there's a lot of functionality that still needs to be added and things that could be improved upon. So hopefully this will lower the barrier of entry to other researchers. The results are promising, but we still have a lot of work to do, and I'll talk about that right now. So the future of Spacetime. As I mentioned before, software is never finished. So there's a lot of things we want to add, updates that need to happen, things that I've been noticing, changes to software, other packages that are required by Spacetime that we need to identify and fix. So we're always going to be continuing development for Spacetime and in both versions. And more specifically, Matt and Brendan Hall and I have been talking about incorporating a lot of their work on natural language and SQL thinking with higher dimensional data sets that are used in space-time to create some more syntax for space-time for actually doing a lot of these operations in a natural human language kind of way, which would be a very cool addition. And I'm excited to work more and talk more with them about that. Also, better NetCDF support for all Google installations. So Google changes the way it handles NC4 files over the different versions, and we want to make sure that people aren't dealing with version issues when they're downloading Spacetime and realizing that their Google version is doing something different. So there's some more work that needs to be done on that. It does work with most versions. And there are recommended versions in the require.txt file. So maintaining the code base, fixing depreciated syntax, and things like that is always ongoing. But I also want to improve demo videos, code snippets, and potentially a new website for Spacetime to host all of these things so that it is all in one place. Currently, at this GitHub Pages site, I have the Spacetime project, which gives a little description, a little information about Spacetime, and then starting with the R package, some documentation, the API, which looks like this, so you can get kind of the syntax and what's in each function, and then as well as some information about known issues and installing and working through some basic coding in Spacetime, some examples. And then the same thing for Spacetime. We have the Spacetime PyPI page here, as well as the API and some more walkthrough scripts and things like that. But I would like to add more videos, more demonstrations, and more code snippets and host them all on a nice, clean website. So that's going to be something that's happening in the future as well. So also we're working on submitting this case study and some methods around Spacetime for publication. We're hoping maybe something like ecography that has that ecologist focus, but also has that computational biology side to it as well. We're beginning to build a development and user base. We're hoping to continue that going forward. We did a little bit of that with Barracuda. We did a great boot camp for a week on data science skill building. Over 100 people attended from various universities. It was virtual and in person. And we did a Spacetime intro in R for that. And it was great. The response was great. I also presented at a PyData event and got a lot of great feedback on how to improve Spacetime and ways, directions to take it, which is great. But again, more of those things, hackathons, conferences, classes, and workshops. I am teaching at UVM a graduate course called Computational Biology, and I'm hoping to do a couple weeks or maybe a week on Spacetime and a week on graphics, spatio-temporal graphics in Python and R. So that's something that I'm hoping to do and hoping to keep Spacetime going and teach it to other people. In addition to that, I'm continuing my work on disease transmission in bees, and I'm always thinking about ways to merge ideas. And a lot of the thinking I've been having around disease transmission has been at the landscape level. And there's a lot of data available, and there's just a lot of ways to think about putting it together. So I'm hoping to use Spacetime and incorporate Spacetime updates and maintenance in future grants that are also using spatio-temporal data. So the idea is to use these like landscape level environmental data to model transmission on the landscape and look at floral diversity and nutrition and all of these things. A lot of these data exist, and hopefully gonna get working on this grant in the next few months. So in summary, I'm excited about Spacetime, spatio-temporal data, disease ecology, bee science, and in general, the opportunity for overlap between these projects. I'm also very happy that you all invited me to come here and give this talk. It was really exciting, and I hope that you enjoyed it and that you'll give me some feedback on directions to take this, things that are useful, things that you don't see as being as useful. And I thank you again. And with that, I'll take any questions that you have. Thank you.
All right, so thank you, Alex. We'll give some people some time to throw some things in the Q&A. The first thing we have in the Q&A is more of a love this talk, gonna try it format here. So that's always a good sign. So we have answered that, and we'll keep the floor open for questions. I don't know, Becky, if you have any questions. I've seen this before because I've been part of development, but I know Becky works in environmental protection, so she might have some thoughts
Yeah.
generally.
Yeah, I can see this applying to a lot of our sort of long-term monitoring data, river and stream data, insect, macroinvertebrate indexes that they've been working on developing. So I think there's a lot of people who would be really interested in this at DEP. I was wondering if you could put the link to the code repository in the chat, Alex.
Yeah, do you want the well, I guess I'll give you the GitHub Pages site because that has links to all of the relevant things, including GitHub repositories, PyPI pages, and things like that. Does that work?
Yeah, that'd be great.
Yeah, we'll send that out to the attendees and all of that. So we have a question. Any thoughts of building a QGIS plugin for simple use cases? So I don't know how familiar you are with GIS software outside of this environment, but something like Arc has a Python background and can leverage Python script. Q
Yep.
also has the ability to do some of that. So that's kind of what this is referencing. So
Yeah, I haven't used much ArcGIS. I use QGIS all the time. I haven't thought about making a plugin for QGIS, but it is potentially a good idea, and I would love to explore it. I'd have to think about how to do that. That's outside my wheelhouse, but yeah, that could be really cool. I have had a lot of people actually, even in my comp bio class, there's somebody who's a geoscientist and first year PhD student, and was curious if we're going to be working in ArcGIS and using the Python bindings of that. And I hadn't thought about doing it yet, but that actually could be a cool way to integrate, you know, QGIS and Spacetime and include kind of a spatio-temporal or GIS module. But
I think that type
pretty
of
cool.
stuff's important because you start talking about the people who use these tools anyway often use the more software oriented ones as opposed
Yeah,
to
the
more the
GUI.
hard coding. So having a direct path between the two of them is extremely beneficial. So
I'll have to look into that. I'll write that down.
we have
Thanks
other
for that
questions for
question.
Alex. So, are you familiar with other work that has dealt with orthogonality, cell size, and extent, such as geomorphic change detection for different platforms? In this case, ArcGIS and GRADS.
I am not familiar with that, and I would love to look into it more. Um, as an ecologist and somebody with a background outside of the GIS world, um, I've always been the focus of this was always to make it something that the average ecologist who finds themselves needing the raster data to incorporate in a model, something um, uh, related to climate data, for instance, or temperature covariates that they might need to add, could easily do that. And so there's this balance in space time between simplicity and complexity, and the output of how complex something can be by trying to make it as simple as possible. So um, if you can think of ways to incorporate things like that into space time and things that would improve the simplicity or make some of these operations make more sense, then that's fantastic, and I'm happy to look it up. Um, will I get a transcript of these comments after? Is there a way to save that out, or will it? Because there's some great ideas
That's a
I'd love
good
to
question.
look into.
I think that when I upload it to YouTube, I believe it does do a transcript of
Great,
both the voice and the Q&A questions. So I'll try and remember
perfect.
to get that to you.
That's great because yeah, I don't think I'll remember everything or have time to write everything down, but there's so many good ideas flying. So
Yeah, but I can speak to that. This type of stuff has happened with this library. So a couple of examples of that. One that Alex didn't show is that we've incorporated things that relate to things like statistical quality control and how we denote points on a line graph in terms of like what are outliers and things like this. It's a thought process that comes from another field brought in to say, well, what would that matter to say an ecologist or something like that. And then we can also talk about, there are opportunities, as he mentioned in the talk, about working with the query by location effects that you see natively in a GIS, how those work relative to raster data, which then gets to the stuff that he referred to with Brendan and I working on. So there are opportunities that these things are being played with all the time.
Yeah, I didn't show the control plot. That software, that functionality is still exists in Spacetime.
Yeah.
Yeah, and it's super useful for looking at long-term climate data. I tried to run it for the this specific data set that I ran through, and since temperature is related to season, and it was just a
Yeah.
big hyperbolic
Yeah.
thing that it didn't make much sense. But
Yeah.
for something like long-term temperature over multiple years, it's a super useful component.
Yep. So we have a question here from Andy. When you write output to disk, how do you handle metadata, specifically related to processing steps like reprojection?
Yeah, all of that is then, so all the outputs are written out as NC4 files. So all of the metadata and projections that are being used during the course of the rescaling are then stored in the NC4 file and then locked into that file. So when you upload it, it'll still map in GIS or QGIS, and then can also be loaded into other geospatial software in Python or R. So it's all still there.
All right. Are there any other questions for Alex right now? You've got an empty queue. So, okay. What do you think about creating cubes out of different data, i.e. predicting not just weather, but plant diversity reduction or disease transmission by bees or something like that?
Yeah, it's super interesting. And Spacetime actually has, so I always talk about Spacetime cubes, and the name of the library is called Spacetime, but it actually is super handy for handling other d-dimensional array data structure kinds of things. So plant arrays could totally be handled if you had site and time as dimensions, and you created kind of a pseudo raster. It wouldn't really be spatially mapped, but Spacetime could still handle it. And you could have that for different species, and actually the metadata could be their relatedness or some other parameter between those things. So if you were looking at one thing that I'm going to be doing and have done a bunch of is floral surveys, and then downloading some bigger data as well, but doing some ground truthing, is to look at the relatedness of flowers on that extra z axis as a phylogenetic structure. And then you can actually look at clades that are similar families that might be being visited more often. There's a whole use case that I haven't really gone over that's related, that I'm writing a grant for right now, that's all about floral mediated disease transmission. So the whole flower component is super interesting to me, and that in land use and pasture areas where you might have lots of high floral diversity, and then areas where there might be monocultures or agricultural components, we're finding that lots of diseases are shared between bees and bee species on those flowers. So that's a lot of the work that I'm planning on doing now. And it would be a multi-cube thing in a model like that. You could incorporate them all into one cube, but it would be kind of unwieldy. So I think the idea of thinking about cubes for purposes in this structure is useful. So you would have like a flower cube that had all the flowers, all the sites, all the times, their relatedness, and then maybe some land use cubes that showed how the land use is changing over time, and some sort of hypothetical model about how those floral diversities are being spread across that landscape for your actual model your simulation to run on, or something like that. There's endless possibilities on that front.
Yeah, so I'll emphasize about that. The thing that I do when I teach data mining is I always talk about methods are agnostic of the place they come from. So like, and that's no place is that clearer than something like data mining with something like k-means clustering, which is all about where something is relative to an abstract space. When we talk about a physical space and we talk about clustering has a way that we view it, but that way that we view it is also applicable in that data mining space as well. It's just we don't have the goggles for it, which makes it harder to physically interpret the visual. but at the same time, the concept is still there. So yeah, a lot of spatial concepts are actually buried within data mining techniques, whether or not people recognize it. So
Yeah, I remember I was in a complex what was the class? It was a modeling complex systems, and the professor pulled up like 9 equations or 8 equations or something like that, and said, for the homework, show me how these are all pretty much the same thing, and they were all uh, different equations from different fields, like engineering, quality control, ecology, chemistry. And one of them was like a Simpson's diversity index. And it was
mhm.
all just basically diversity indexes. Just, you did a little manipulation, like, oh, that's the same thing. And it all fell out that they were pretty much the same math. And yeah, so, there's lots of ways that you can use things. And trying to reuse tools that are meant for one thing for another is a great way of innovating. So hopefully there's lots of ways that you can think about cubes, d-dimensional data sets that space-time can handle, and do cool science with it.
And I don't want to speak for Alex, but I know that this tends to be how Alex thinks a lot. If there are things in the community that make sense for analytical pathways and frameworks and whatnot, please keep open dialogue because this is how these systems get better. So one of the benefits of things like our packages is that they're developed by the people that use them more so than they're developed by software developers. So you start to see them organically take on the language of things that come from those fields. So it's important for all of you who have interest in this to keep the lines of communication open with Alex. And I know that Alex is receptive to that. So please do that because that helps everybody along the way. So
Yeah, that's great. I mean, my goal for this has always been to try to develop an open source ecosystem around this that has a developer community. And we've written Pose grants for that, unsuccessful, unfortunately, but with some great feedback. We're hoping to try again. So Pose is a NSF grant designed to help facilitate building a community around open source software. So things like, you know, your open line of dialogue about how you would use this and functionalities you wish to see, or issues that you find, meaning understanding that software is never finished, as I said. That's super great. There's a number of edge cases that we could probably find where new functionality should be added, or new questions that somebody might have that Spacetime could be adapted to help answer or help solve with just a few tweaks. So um, let me know.
all right, so we've hit 1 o'clock. I don't see any additional questions. So Alex, do you mind if we share your email when we send out the stuff from the talk?
No, not at all. Please do. And I just might have gotten distracted, and I want to make sure I didn't send that. Let me put it in the chat. Yeah, here we go. Yeah, so there's the GitHub pages for Spacetime.
All right, so I want to thank Alex for his time this afternoon, and thank you all for your attentiveness and participation. So we'll catch everybody at a future event. And Alex, have fun with all the stuff going on with the bees and the teaching. So
Oh, thank you. Thanks for having me, and thanks for all the